Imagine racing alongside a beam of light is photons zipping through the cosmos. What would you see? These questions consumed a young Albert Einstein at the turn of the 20th century. Little did he know his quest for answers would shatter our understanding of space, time, and reality. Before Einstein, physicists viewed the universe through a Newtonian lens, a world of absolute space and time. But Einstein, with his elegant equations and thought experiments, unveiled a far stranger and more wondrous cosmos. His theories of relativity would forever alter the course of science and reshape our place in the universe. Albert Einstein, born in Ulm, Germany in 1879, was not a child prodigy. In fact, he was a late talker, leading some to question his intelligence. His early education was marked by a disdain for rote learning and a deep fascination with math and physics. Despite his intellectual gifts, Einstein struggled to find his footing after graduating from the Swiss Polytechnic Institute. Academic positions eluded him, and he found himself working as a clerk in the Swiss patent office in Bern. This seemingly ordinary job provided an unexpected gift, the freedom to ponder the mysteries of the universe. Free from the constraints of academia, his mind soared, grappling with the fundamental nature of light, gravity, and the very essence of space and time. The year 1905 stands as a landmark moment in the history of science. It was a year that would forever change our understanding of the universe and our place within it. This pivotal year is often referred to as Annus Mirabilis, or the Year of Miracles, due to the extraordinary scientific breakthroughs that occurred. At the age of just 26, Albert Einstein published 4 groundbreaking papers, each one a masterpiece. These papers would go on to revolutionize the fields of physics and cosmology. Despite his youth, Einstein's insights were profound and far-reaching, challenging the established scientific paradigms of the time. Yet he accomplished this extraordinary feat while still working as a humble patent clerk. His day job involved examining patent applications, a task that was far removed from the lofty realms of theoretical physics. Nevertheless, Einstein's mind was constantly at work, pondering the mysteries of the universe during his spare moments. Among these works was his paper on the special theory of relativity, a revolutionary concept that challenged our fundamental understanding of space and time. This paper introduced the idea that the laws of physics are the same for all non-accelerating observers, and that the speed of light within a vacuum is constant, regardless of the motion of the light source or observer. Einstein proposed that the speed of light in a vacuum is constant, regardless of the motion of the observer or the source of light. This was a radical departure from the Newtonian mechanics that had dominated scientific thought for centuries. The implications of this theory were profound, leading to a new understanding of the relationship between space and time. This idea had profound implications, leading to the mind-bending concepts of time dilation and length contraction. Time dilation refers to the phenomenon where time appears to pass more slowly for an object in motion compared to one at rest. Length contraction, on the other hand, describes how objects appear to contract in length as they approach the speed of light. His work on the photoelectric effect Brownian motion and the equivalence of mass and energy were equally groundbreaking. The photoelectric effect demonstrated that light could be thought of as both a wave and a particle, laying the groundwork for the development of quantum mechanics. Brownian motion provided empirical evidence for the existence of atoms and molecules, which were still a subject of debate at the time, and the equivalence of mass and energy. This was famously encapsulated in the equation EMC2, which showed that mass and energy are interchangeable. This equation revealed that a small amount of mass could be converted into a tremendous amount of energy, principle that would later be harnessed in nuclear power and atomic weapons, laid the foundation for quantum mechanics, and revealed the astonishing amount of energy stored within even the tiniest particles of matter. Einstein's work in 1905 not only transformed our understanding of the physical world, but also paved the way for future scientific discoveries. His theories continue to influence and inspire scientists to this day, proving that the Year of Miracles was indeed a turning point in the history of human knowledge. Section 4. Unlocking the Secrets of Space and Time. Special Relativity Explained. In this chapter, we delve into one of the most groundbreaking theories in the history of science, a theory that has fundamentally altered our perception of the universe and our place within it. Einstein's special theory of relativity, published in 1905, revolutionized our understanding of the universe. This theory was not just a minor tweak to existing ideas, but a radical shift that challenged the very foundations of classical physics. Before Einstein, the prevailing view was that space and time were absolute, unchanging entities. However, Einstein proposed that space and time are interwoven into a single continuum known as spacetime. At its heart lies a deceptively simple idea. The speed of light in a vacuum is constant for all observers, regardless of their relative motion. This means that no matter how fast you are moving, whether you are speeding through space in a rocket or standing still on Earth, you will always measure the speed of light to be the same. This constancy of the speed of light is a cornerstone of special relativity and has profound implications for our understanding of the universe. This concept has mind-bending consequences, challenging our everyday intuition about space and time. For instance, it implies that time and space are not fixed and absolute, but can stretch and contract depending on the relative motion of observers. This leads to phenomena that seem to defy common sense, such as time dilation and length contraction. Imagine two observers, one standing still and the other on a moving train, both observing a beam of light. According to classical physics, the observer on the train should measure the speed of light to be greater than the stationary observer because the train's motion adds to the speed of light. However, this is not what happens. According to classical physics, the observer on the train should measure the speed of light to be greater than the stationary observer. This is because in classical mechanics, velocities add up. If you throw a ball while on a moving train, the speed of the ball relative to the ground is the sum of the speed of the train and the speed at which you threw the ball. But light behaves differently. However, Einstein's theory postulates that both observers will measure the speed of light to be exactly the same. This is because the speed of light is a universal constant, unaffected by the motion of the source or the observer. This idea was revolutionary and counterintuitive, but it has been confirmed by numerous experiments. This constancy of the speed of light leads to the bizarre but experimentally verified phenomena of time dilation and length contraction. Time dilation means that time actually slows down for objects in motion relative to a stationary observer. Length contraction means that objects in motion contract in the direction of their motion. These effects are not just theoretical. They have been observed in experiments involving particles moving at high speeds and in the precise timing of GPS satellites, which must account for these relativistic effects to provide accurate positioning data. For example, GPS satellites orbiting the Earth experience time slightly differently than we do on the ground. Their clocks run faster due to the weaker gravitational field at their altitude, but slower due to their high speed. Engineers must account for these differences to ensure the system's accuracy. Similarly, particles accelerated to near light speeds in particle accelerators exhibit time dilation, living longer than they would at rest. These real-world applications underscore the practical importance of understanding special relativity. Special relativity has also deepened our understanding of the universe at large. It has paved the way for the development of general relativity, which describes how gravity affects the fabric of space-time. Together, these theories provide a comprehensive framework for understanding the cosmos, from the smallest particles to the largest structures in the universe. As we continue to explore and uncover the mysteries of space and time, the principles of special relativity remain a guiding light, illuminating the path to new discoveries. Session 5. Warping the Fabric of the Cosmos. General Relativity and its Profound Implications. In 1915, a decade after his groundbreaking work on special relativity, Albert Einstein published his theory of general relativity, a monumental achievement that provided a new understanding of gravity. This theory was not just an incremental step, but a revolutionary leap that changed the way we perceive the universe. Einstein's work built on the shoulders of giants like Isaac Newton, but it also diverged in a way that was both radical and profound. While Newton's laws had described gravity as a force acting at a distance, Einstein's equations suggested something entirely different. Unlike Newton's view of gravity as a force acting across empty space, Einstein envisioned gravity as a curvature in the fabric of space-time itself. This was a paradigm shift that required a new way of thinking about the universe. Imagine space-time as a flexible, four-dimensional fabric. When a massive object, like a star or a planet, is placed on this fabric, it causes a dent or a curve. Smaller objects moving nearby will follow the curves created by these massive objects, much like marbles rolling around a dimple on a stretched sheet. Massive objects like stars and planets warp the space-time around them, much like a bowling ball placed on a trampoline curves the fabric beneath it. This warping effect is what we perceive as gravity. The more massive the object, the greater the curvature it creates, and thus the stronger the gravitational pull. This analogy helps us visualize how gravity works in Einstein's universe, but the actual mathematics behind it is far more complex and elegant. This curvature of space-time dictates the path that objects follow, explaining why objects fall towards the Earth and planets orbit the Sun. In Einstein's view, planets are not being pulled by an invisible force, but are instead following the curved paths laid out by the warped space-time around massive objects like the Sun. This concept also explains why astronauts in orbit experience weightlessness. They are in free fall, moving along the curved space-time created by Earth. General relativity has had a profound impact on our understanding of the universe, leading to the prediction of black holes and the bending of light around massive objects, known as gravitational lensing. Black holes are regions of space-time where the curvature becomes so extreme that not even light can escape. Gravitational lensing, on the other hand, because when light from a distant star or galaxy is bent around a massive object, like a galaxy cluster, creating multiple images or distorted views of the original light source. Einstein's theories of relativity have revolutionized our understanding of the universe and continue to inspire scientists and dreamers alike. From the GPS systems that guide our daily commutes to the exploration of distant galaxies, the implications of general relativity are far-reaching and profound. As we continue to explore the cosmos, Einstein's legacy lives on, reminding us that the universe is a place of wonder, complexity, and endless possibilities. Einstein's theories didn't just revolutionize physics, they laid the groundwork for future discoveries that continue to shape our understanding of the universe. Today, the legacy of Einstein's work is evident in some of the most groundbreaking scientific advancements and explorations. One of the most exciting areas of research influenced by Einstein's general relativity is the detection and study of gravitational waves. These ripples in the fabric of space-time were first predicted by Einstein over a century ago, but were only directly observed in 2015 by the LIGO and Virgo collaborations. The detection of gravitational waves opened a new window into the cosmos, allowing scientists to observe cataclysmic events like the collision of black holes and neutron stars. These observations have provided invaluable insights into the nature of gravity, the behavior of extreme objects, and the dynamics of space-time itself. Another remarkable confirmation of Einstein's theories came from the Event Horizon Telescope project. In 2019, this global network of telescopes captured the first ever image of a black hole's event horizon, the boundary beyond which nothing can escape. This achievement was a testament to the power of Einstein's equations, which had predicted the existence and properties of black holes long before they were observed. Einstein's work also plays a crucial role in our daily lives. The Global Positioning System, GPS, relies on the principles of both special and general relativity to provide accurate location data, without accounting for the time dilation effects predicted by special relativity and the gravitational time dilation described by general relativity. The GPS system would quickly become inaccurate, leading to navigational errors. As we look to the future, Einstein's theories continue to inspire new generations of scientists and explorers. From the quest to understand dark matter and dark energy to the search for habitable exoplanets, the principles of relativity remain at the heart of our exploration of the universe. Einstein once said, "The important thing is not to stop questioning. Curiosity has its own reason for existing." His relentless curiosity and profound insights have left an indelible mark on science, reminding us that the pursuit of knowledge is a journey without end. Thank you for joining us on this exploration of Einstein's revolutionary ideas and their lasting impact. If you enjoyed this video, please like, subscribe, and hit the bell icon to stay updated with our latest content. Together, let's continue to explore the wonders of the universe.